Hey everybody, Mr. Carlson here. Let's talk about kinetic energy and temperature of gases. So let's say I've got a container here, and in this container I've got a sample of gas, and within there we know that those particles of that gas are in constant motion. They are moving around all the time, bouncing off the walls of the container, bouncing off of each other. And some of them maybe have some faster velocities or they're moving quicker than some other ones, but on average they have a specific amount of energy between them all. And it's the kinetic energy, which, remember, kinetic energy, when we're talking about the kinetic energy, we're talking about the energy of motion. Energy of motion. And so these are all moving, and so therefore this container has a specific amount of energy because of that motion of those particles. The way that we measure that, though, how do we measure the amount of kinetic energy? Well, first of all, let's define what mathematically what kinetic energy is. Kinetic energy is equal to, so if I wanted to figure out, like, let's say the amount of kinetic energy that one particle has, kinetic energy is 1/2 times the mass times the velocity squared. So mass, meaning how much stuff we have, right? Mass times the velocity. If I take the mass, 1/2 times the mass times the velocity squared, that gives me how much kinetic energy I have. And so if I want to measure how much kinetic energy like a specific particle has, what I need is its mass, and I need how fast that it's moving in order to figure out how much kinetic energy an individual particle has. Now, here's another thing. We can relate this to temperature because essentially temperature is essentially a measure of the kinetic energy or the average kinetic energy of these particles in here. So, in fact, let's write that down. So the Kelvin temperature is directly proportional to the average kinetic energy, and we'll just leave it at that actually. The Kelvin temperature is directly proportional to the average kinetic energy. In other words, Ke is proportional to temp in Kelvin. So if I were to take a thermometer and I were to put a thermometer in here and I were to measure what the temperature is, what I'm essentially measuring is what is the average kinetic energy of these particles, because these particles are going to bump into this thermometer, and as they do, as they hit this thermometer, they're going to transfer some of their energy to the thermometer, and that's what makes the liquid in the thermometer move up, right? Now again, it's the average kinetic energy because not all of these particles in here are moving at the exact same speed. So when I measure the temperature, I'm measuring what's the average velocity of these particles in here. Not all of them are going to have that exact velocity, but what are most of them, essentially, what are most of these particles in here? What speed are they moving at within that container? So let's think about it like this. Two samples of gas at the same temperature, if I have two different samples of gas, like let's say I have hydrogen gas and nitrogen gas, if they have the same temperature, that means they have the same average kinetic energy. But that does not mean that they have the same velocities. They do not have the same velocities. And that's because they have different masses. Let's visualize this. So let's say I have some hydrogen gas, H2 molecules in this container. Let's say these containers are the same size and they are at the same temperature. Since they both have the same temperature, they're both at 300 degrees Kelvin, that means the average kinetic energy of both of these is the same. Okay, so if I were to measure the average kinetic energy of this and this one, they're going to be exactly the same. But we would actually see that most of the particles in the H2, those ones are actually going to be moving a lot faster on average. On average, most of these are going to be moving a lot faster. So some of them moving kind of slower, but most of them moving a lot faster compared to the N2. The N2 molecules are going to be moving on average a little slower, a little bit slower. Some of them moving faster, but for the most part, on average, moving slower. But they both have the same temperature. And how could that be? And the reason being is because if we go back to this equation up here, remember we have to take into account the mass of these particles. Okay, so the kinetic energy is the same for each one, but notice that nitrogen, these molecules of nitrogen are much bigger. Nitrogen has a bigger molar mass than hydrogen does, so these hydrogen molecules are much smaller. And so these H2 molecules, on average, are going to be, their velocity is going to be a lot higher velocity. It needs to be in order to be at 300 K, but for N2, these molecules don't need to be moving as fast in order to be at 300 degrees Kelvin because their mass is much bigger. And so they have the same kinetic energy, but they don't have the same average velocity. H2 is going to have a much higher velocity because it's got a smaller mass, and that's what we have written down here. So both have the same kinetic energy because they have the same temp, but which one has a higher average velocity? It's going to be H2 because it has a smaller mass. So that